Okay, so we're going to continue what we talked last time. Just a refresh. So last time we're talking about we started to introduce the statistic thermodynamics. So we introduced three very key concepts. One thing is, what we say is the micro state, okay? The macro state, that means the one we can measure or see by our naked eye, by the ruler, by the thermometer, by whatever, okay? So typically we have the thermodynamic parameter we introduced so far are all correlated to the macro states, okay? So basically the volume, temperature, pressure, even the entropy, enthalpy, whatever, okay? So you can see that this kind of parameter apply all kind of the thermodynamic systems, whether it's gas, liquid, solid, doesn't matter. Okay, we can use all this one to describe the states, the thermodynamic states of the system, no matter what type of matter it is. Okay, but the reason we go to statistical thermodynamics, the main reason so far is we want to explain what the entropy is. And to understand that, we also introduce another concept we call it the distribution, right? So what is distribution? We introduced that. We'll give you one analogy next time. We talk about parking garage, right? So we have the parking garage, and on each level we have the first level we have N1 number of cars, the second one N2, N3, okay? Then the total energy of the system is equals to what? Equal to sigma I, Ni, Ei, okay? The Ei is just the energy of each of the states, okay? And this is the number of the cars parking in the respect floor or parking level in the garage, correct everybody? Oh, by the way, I took your marker away last time.
Is this still full?
No, I took your marker. I forgot to return it back to you. That's fine. It's in my office. Do you have a new one?
No, just hang on to it before,
Okay. Anyway.
in case yours run out.
Okay, so just in case this one's not working, anybody can provide me another one marker? We don't have any marker provider at the time? Okay. It seems I lose my credit among you guys. Sorry about it. But anyway, so let's continue. Oh, by the way, everybody see the homework, right?
Yes.
Have you started doing that? Is that hard or simple? What does that mean? It's so easy, right? A piece of cake.
See when we get farther in it.
What's that?
We'll see when we get farther in it.
What's that?
We'll see when we get farther into it.
How many questions have you finished?
2.
I think you can finish the first question without even look at it, just check the checkbox. But you need to finish it, okay? If you do not finish it, I will make sure that your midterm will become a disaster. But for sure, midterm will not check box, okay? Do you know this concept? Yes. Do you know? Yes. Then you pass. No, it's not that way, okay? There's no check box. Okay? Anyway, let's go back. So the number of the occupation on each of level, we call them the distribution, okay? We call them the distribution. Distribution is N1, N2, N3, blah, 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 okay? And it's the number of the occupants, okay, or cars on each of the parking garage level, okay? We do not care what type of car it is, okay? Among the N1, it can be Toyota, it can be Honda, it can be Hyundai, it can be like the Ford, it can be like the Ram, whatever, that matter. We only care about how many cars there, okay? This is, we call it distribution. Okay, how many cars parking on each of the parking garage. And below it is the macro states, okay? Is the micro state. Micro state that we start to care about what specific car parking on each floor. You know what I'm saying? So probably we have one student parking on this car, and student A parking his car on the garage on the first floor, and student B parking on the second floor, and on the second floor we have C. Okay? And we have another state, something like the A, C, and B. Okay? They are different microscopic states. Okay? However, they belong to the same distribution. Is that clear? because we cannot change the distribution without changing the number. And we also introduced that if we consider the total energy of the system is conserved, that doesn't change. Okay, this is the first law of thermodynamics. And the total number of the particle or the car doesn't change. Then we have these two restrictions, right? These two restrictions. And then we can find that under this restriction, for each of the distribution, we have different numbers of microstates. Correct? So remember last time we talked about the distribution in that way? So we have the one particle, one. This is A, B, and C. Okay, we can flip the order. Okay, we can flip the order. The total combination, not total combination. What's the name of that word? Permutation, right? Is what? Is the factorial of 3, right? The total number of 6. Number of 6? That's 6? Anyway, so it's 6, okay? But if you consider this type of distribution, the total number is 3, right? And this type of distribution, total number is probably 1. Anyway, so we'll give you this example. That means under the same microstate, we have different types of distribution. And under each distribution, we have different kind of microstate or macro configurations, right? So eventually, which distribution we eventually or experimentally observe depends on how many microstates is there, right? According to but basically, the distribution which gives us the most microstates, the number of microstates, has the highest possibility to be observed. Correct? Understand? Has the highest possibility to be observed. And this possibility typically corresponding to the distribution has the highest possibility to determine the microstates. Okay? That's basically what we observe. Any questions? We're just talking about parking garage, right? And if we expand our model or this kind of argument to physical systems, for example, for the ideal gas. Okay, let me briefly to make it more clear. Okay, so basically we have a microstate. Okay, and then the microstate have two requirements. One is the conservation of the energy. The other is the conservation of the particle numbers. Okay? So this is, basically that one. Okay? And then you can see that if we have these two conservations, we already introduced the concept of distribution, right? So basically, the distribution beside the microstate. Correct? This is the distribution. Correct? And of course, we have different types of distributions. And for each of the distribution, we have multiple configurations, right? We have multiple macrostates. Okay, more macro configurations. Okay? For example, we have the configuration looks like this. We have the configuration looks like this. And we can have the configuration looks like this. Right? So this is on your textbook. You can find something. Okay? This is just the version in textbook. Okay? So, and then for this one, we have only 1, for this one have 6, for this one have 3, right? So, then the distribution which gives us the most number of macrostates is the most possible distribution, right? And from the most possible distribution, we can calculate the macrostates. Okay? I hope this one can make me understand the hierarchy structure. And then let's use this kind of the argument to analyze what happened to the ideal gas, okay? Let's give them a number, okay? This way we can call it the section 1, the micro versus the micro states, okay? Okay. So then we can talk about, then we can apply this kind of argument to the ideal gas, okay? The chapter number here. Okay. Microstates and distribution of ideal gas. Okay. Of ideal gas. We already mentioned part of it last time. So for the ideal gas, we can still generate something like the parking garage, okay? We have the parking levels, parking floor, parking garage, okay? Okay, the floor, ground floor, first one, second one, third one. Okay. And of course, we know that for each of the parking garage, each of floor, how many parking spots do you have? Only one or several? Several, a lot of them, right? So on each of the energy level, we have something like this. Okay. We have a lot of parking spots on the same level, okay? And regarding to the ideal gas, what does that mean? What does that mean? Remember last time we talked about the energy of the ideal gas is just the momentum or just the kinetic energy, right? Just kinetic energy. It means how fast the molecule is moving, right? And I can move that fast in this position. I can also have the same speed on this position. I can also have the same speed along this direction, along this position, right? That means if you have a whole tank of ideal gas, if the particle have exactly the same velocity, it can be anywhere. Correct, everybody? So that means the particle has the same velocity. It can be here, right? This, for example, the energy here is E2. It can also be here, right? It can also be here. It can anywhere, right? That means if they are on the same energy level, it can sit on different position, okay? And the different position corresponding to the different parking spots, okay? Is that clear, everybody? Okay, and then, but you know that for the ideal gas, we have a whole tank, right? The energy is not like the isolated, okay? Discrete, it's continuous distributed, right? Energy can be 1, 1.1, 1.12, 1.13, something like that. So instead of the label them in that way, so we just probably define something like this. So the energy distance between neighboring level is just like the dE, okay? Delta E, very small amount. Okay, and last time we talked about the dpx, dpy, dpz. Forget about it. It's probably not very necessary for us to introduce the concept. So in order to avoid any kind of confusion or further expand our topic, let's just stick to dE, okay? And I can probably briefly introduce why we introduce dpx, dpy, dpz, if necessary, okay, in the future discussion. But right now, let's stick to it. Is that okay? And how many parking spots on each of the level, okay? So we don't know, right? But we just assume, okay? On each of the parking floor, we have a total number of omega I, okay? We have total number of omega I. We still like omega 1, E1, we still label it. That makes the job easier, okay? So on the first floor, we have total number of omega 1 parking spots. Omega 1, omega 0, omega 1, omega 2, omega 3 parking spot. Okay? So then, right now we have already built our garage, right? This is the structure of the parking garage. Right now, let's put the particle into it, okay? Let's put the particle inside. The one key assumption is, let's assume the gas particles are distinguishable. Okay? That we can tell the difference from each other. We can distinguish different particles. Although we have all tank oxygen, but we still can distinguish them. Let's assume that, okay? Although this is not true. And at the end of the class, I will let you know why this is not true, okay? But first of all, let's assume this makes our calculation easier, okay? This makes our calculation easier. Okay? Because when we talk about this kind of picture, the ABC particles are distinguishable, right? And then let's follow the same logic here to assume that we can distinguish different kind of gas particles, okay? That's the first assumption. The second one, multiple particles can occupy the same parking spot. This is very counterintuitive, right? Multi-particles can occupy the same parking spot. It's really strange, right? That means on this parking spot we can put one car, we can put two cars, three cars without it. Right? Again, the reason we want to have this definition is we want to make the calculation easier, okay? But it doesn't change the conclusion. But of course, do you know we have two types of the fundamental particles? We have two types of fundamental particles.
What was it?
Huh? Huh? Yeah, louder.
Bosons and fermions.
Yeah, do you know what's the difference between them? Anybody know what's the difference between boson and the fermion? We have two types of particles. Okay? One is we call is the boson. The other we call is fermion. Fermion. Okay? So basically, this behavior, if the particle can occupy the same parking spot, this kind of particle we call them boson. Okay? That means no matter how small the space, we can squeeze as many particles as possible. And then the other type of the particle we call is fermion. The fermion is just like your car. One spot, only one car. Okay? You cannot stack the car in the same spot. But right now, let's confine ourselves to the boson. Okay? Basically, this kind of picture is a semi-classic boson picture. Okay? Because boson itself is not distinguishable, but we still assume them distinguishable to make the calculation easier. Okay? So if you want to know more about the boson and fermion, we can talk about it, but not too much. So to understand the boson and fermion, I can give you an example. So for most of the molecules, the fundamental particles, neutron, proton, electron, they are fermion. Okay? The fermion cannot occupy the same space. You cannot put two fermions in the exactly same space. Okay? So they always separate from each other. Okay? So what's the consequence of this kind of repulsive behavior? It's going to help us to build the structures. Okay? For example, what is structure? For example, you have a crystal. You can see that all the molecules are arranged in a really good order, right? Molecules. I mean, when you study, have you learned the class we call it the structures of materials? I think this class talking by Dr. No, it's not.
Professor Fang mistake.
Professor
Fang.
Okay, the associate chair, right? Did you mention that the crystal structures? What's that? The reason why we have crystal structure because all the fundamental particles are fermion. Why is like this? It's like this, okay? First of all, let's ask you. Consider I am a fundamental particle. Do you think I'm a fermion boson? I'm definitely fermion, right? Because you cannot assume so many people stand exactly on the same position but they overlap each other. Impossible, right? Okay, right now consider you have the empty elevator. You went to the elevator. You are the only one in the elevator. Where are you going to stand? Anywhere. And then on the second floor, another person comes. What's the highest possible configuration in the elevator? You do not know each other, okay? What's the highest possibility?
Near the road.
2 corners, right? Third one come. What's the option for the third one? Probably 3 corners. And fourth one come, 4 corners. And the fifth one come. Where the first one come stand? In the center, right? So what's the structure? It's face center cubic structure. Exactly, right? So because this kind of, people do not want to have very close distance to each other, can help you spontaneously build up the structure. This is exactly the same for materials, okay? Don't laugh, this is exactly the physics principle, okay? But what about boson? Boson is just like a jelly, you just put everything actually craft together. So what's the example of boson?
Couples.
Huh?
Couples.
Not really, because even you have with your wife or husband or whatever, I mean your partner, you still not overlap each other. One example is the light. The light. You know what I'm saying? The light. Think about it, for the laser, this kind of very large beam. Okay, think about you have a laser pointer to generate beam like this. You can always use a lens to concentrate it, right? And you can couple it to fiber. I mean, what's a laser? Basically, laser is kind of like you have large amount of the photons in the same states. Okay, that's the laser. So basically, it's like boson. So what's the use of boson? Boson typically used for information transformation. Okay, and boson is also help the fermion to exchange the interactions. But doesn't matter. But as long as you know we have 2 types of particles, boson and fermion, that's good enough. Okay. But anyway, so this model, if several particles can occupy the same spot, this one is boson. Fermion, everybody here is boson. Fermion. Okay, so then we start to drop these kind of particles, okay, with these 2 assumptions into the system. Let's see how it looks like. Okay, now let's assume we have a distribution like this. Let's assume we have a distribution like N1, N2, N3, N4, Ni. We have this type of distribution, right? We want to know which distribution corresponding to the highest number, give the largest number of possible microstates. And then this specific distribution is the most possible distribution. Correct, everybody? The distribution which gives us the highest number of the microstates is the highest possible configuration, correct? So we need to calculate, okay? We need to calculate how many specific microstates corresponding to this distribution. Okay, let's see the draw. So first of all, we need to fill the N1 particles. No, sorry about it. Let's add something else. Let's add N none, okay? Because I already put none here. Anyway, N1, 0, 1, 2, 3, 4. That's good. First of all, let's put the N0 particles in the E0 energy level. Okay? Got the points? We just randomly put them here, right? Randomly put them here. So how many different kind of method we put N0 particles in the E0 level? How many different ways? It's just like we put N0 particles in number of omega-1 boxes, right? How many different ways to do the job? What?
Permutation.
Sure. Okay, let's continue. We are talking about the particle that occupy the same space. Okay? So we take the first particle out of N0. So how many different ways for us to put this one particle around omega-1 box, omega-0 boxes?
5 ways.
Huh?
5.
No, this is not 5, okay? I mean, this is just something. It's
Oh.
it's omega-0. It's not like specifically 5. Okay?
Okay.
It can be 6, 7, 8, that doesn't matter. Okay, I just randomly put some
Okay.
here.
Okay. Omega not.
How many different configurations? How many different ways?
Omega 0.
Omega-0, right?
Yeah.
This is for the first one. And then I put the second one on top of it. How many different configurations? Still omega-0, right? Because I can put the first particle here, I can put the second particle here as well, right? Remember when each of the parking spots can be occupied by multiple particles. And 3, the third particle, right? So that means the total different kind of the different occupation method or like microstate corresponding to N0 in the E1 is what? How many numbers? Is the omega 0 to the order of N0. Correct, everybody? Right? This is how many different ways you can put the N0 numbers of particles in the E0 state, energy level, right? The same thing to the second one. Is that correct? Right? Is that right, everybody? So, in that case, you know what? The total number of the microstate is what? Is a pi I omega I and I. Correct, everybody? This is the total number of the. Is that right? Right. This is the how many different kind of ways we can put N1 particle in the first one and to the N1 to the first one and to the second one. Okay. But we still have not considered we can exchange the particle between these two, right? Remember? Right now we already separate them. Right now this is the combination. This is the the combination, right? But we still need to consider the exchange between particles among the N1 and N2 and N3, right? Understand something? That means we need to separate total number of N particles into these groups, right? And how many ways we can separate them? It's just like this, okay? So first of all, we need to take for the first 4, we need to take N particles out of N, right? How many different combinations for me to take N0 particles out of total number of N? Is the Cn N0. Correct, everybody? Right? That means for the first one, we have the combination of the Cn N0. Okay? What about for the second one? Since we're already taken N0 out of N, so we only have N minus N9, the total number of particles, right? And we take N1 out of it. Correct? And for the third one, the same thing, N minus N0 minus N1 and N2, right? And then for that one, then we need to have another factor here, is I. Cn minus I minus Ni minus 1 and yeah. 1 and let me write I Cn this kind of complicated expression. Right. It's complicated. That means we need to do this kind of the pi. That means we do the production all of them, and the Cn minus remove all the sum of all the N particles before the S level, and do the combination. But we can make it simpler. Okay? We can make it simpler. So what's the expression of this combination? The Cn and non. What's the expression of it? is the factor of n minus none and n minus. Is that correct?
Yes.
And then the Cn minus a none n1. This one equals to what? Equals to n1 minus n9 factorial, and then n1, and then n minus n9 minus n1. Correct? And for the third one, Cn n9 minus n1 and n2. This one equals to what? Equals to n minus n9 minus n1 factorial n2 and n minus n9 minus n1 minus n2. Correct? Then we need to do the production of it. Okay. So you see that? Is everything good?
Yeah.
Okay. If this one times this term, you can see the denominator and this one got to cancel each other, right? So we can, let me put it here. The whiteboard so small. So we know that the Cn n1 times Cn minus n1 times n minus n1 2. Then this term equals to what? Equals to n9 minus n9 and n1 and n minus n9 minus n1. Right? And this one is n minus n9 minus n1 2. And this is n minus n9 minus n1 minus n2. Okay, so we have continue the job. So this term cancel each other, cancel each other, cancel each other, cancel each other. Now, of course, this one will cancel with the following terms, right? Eventually, what we have is something like this. It's n1 and pi yeah, pi I n I. Correct? And because of that, this kind of awkward expression will become simplified. This term simply equals to, although it's not very simple. Yeah, correct? Briefly summarize, not briefly summarize, yeah, briefly summarize. So that means for a specific distribution we have a total number of n pi I n I somebody donate another marker? Nobody? Oh, that's too thin. Anyway, I tried my best to make it the reason that I think you can see when writing, but I'm just writing down myself. It's difficult to read on the whiteboard. Anyway, so is that clear, everybody? Let me make the concept, the key concept more clear. Okay. So we know that right now you know what's the concept of energy level, have you? It's a parking garage floors, right? You know what I'm saying? So we have the parking garage looks like this. Okay? Whatever. So then we have what? This is EI. So the EI, we give the name, we call this one is the energy level. Okay, it's a parking level, but we're talking about energy, like the energy level. We call this parking spots, right? But most specifically, that is one occupation space, okay? And know how many occupation space on this parking on this energy level? We have totally omega I, right? Right? Omega I. So omega I, we give a name. We call it the degeneracy. How to spell degeneracy? Degeneracy. I think it's degeneracy. Probably spelling like this. Okay, degeneracy. That is the how many different possible states share the same energy level. Okay, share the same energy level. Okay. Have you heard about this kind of terminology called degenerated state? Have you heard about this terminology? So we say that two states are degenerated. What does that mean? This kind of physics people always want to give very fancy terminology. That means they have the same energy. Okay? Degeneracy. Okay? The number of degenerate states on the energy level is degeneracy. Okay? So omega I is degeneracy. Understand what I'm saying? This one doesn't talk on our textbook. Other textbook, they ignore this term. Okay? On the textbook, they ignore this term. But that's the reason we got quite a lot of information got missed. But we should have that one. Okay? Anyway, so then the question is, for each of the distribution, we can calculate the number of the possible states in that way. Right? The question is, which distribution is the one we actually observed in our experiment? We already mentioned, right? So the distribution we actually observe is the one corresponding to the largest number of possible microstates. Correct, everybody? So we need to change the Ni to make this one reach the largest number, right? To make this one reach the largest number, okay? We can define a function, okay? It's just like a function like this. Fni equals 2 right? It's a function of 9, correct? The number of the microstates is a function of the 9. It's a function of the distribution, right? We want to find the largest number, the largest value of it, correct? How do you find the largest value of the function?
Differentiation.
Yeah.
0.
Exactly. Take the differentiation, okay? Right? So this one will give us the maximum number, right? Or a minimum number, right? But we know the minimum number is 0, so we don't care. So we just want to find the largest number, okay? So the next job for us to do is to find which value of 9 corresponding gives us a 0 first order derivative. Correct, everybody? So this is our job. Then the problem comes, okay? So think about it. So as you mentioned, we prefer to have a curve or a surface, whatever, right? We have, I mean, for most of the functions, they are continuous functions, right? Sine, cosine, ln, e to the order or something. But this is just discrete, right? They're isolate numbers, right? They're not continuous, right? How can I fix the issue? I mean, think about it. You simply do not know how to do the first order derivative of this function, right? How to do the first order derivative? There's no way, right? Because then it's not function. It's a function, but it's not continuous function. So we don't have definition of the derivative, right? So in order to solve this equation, in order to solve this problem, we make the one approximation. We make one approximation. The approximation is like this. We need to introduce a concept. We call it Stirling. Stirling approximation. So what that tells us? It tells us ln n factorial approximately equals to n times ln n minus 1 plus half ln pi n if n much larger than 1. Okay. Got that point? So by use
Is that 1 over 2?
is 1 or 2. So by do not ask me why.
Is it n minus 1 inside the line?
Is inside. No. It's ln 1 minus 1. It's not inside the ln.
Oh.
N times bracket ln 1 minus 1. Okay? This is it's not n minus 1. It's not ln bracket n minus 1. Right? Am I right? Oh, hold on. I think I made a mistake. Hold on. Yeah, you're right. Luckily, nobody checked my final examination. How do you remember that? I mean, how do you know this mistake? Okay, anyway. Okay. And let me see. Give me a second, okay? Let me check whether you're writing right or not. Give me a second. Can I check online? What's the sign? No. I think it's not like this. No, I think it's still like this. I think it's this.
Yeah.
I think it's still this. No. Okay, it's still like this. Anyway. Just be very scared. Anyway, so if n is much larger than 1, if it's much larger than 1, then compare, okay? Compare this term. And which one is larger? These two terms. This one is actually much larger than that one, right? So that means we can approximately ignore this term So this one is to the order of n. Of course, it's to the order of n. But this one to the order of log n, right? So this is much smaller, right? So in that case, if this one is much larger than 1, so we can further do the approximation. We can simply equals to n times log n minus n, minus 1. Okay? Or to make it more clear, so it's n times log n minus n. Okay? Is that correct? So this is the approximation, right? So then we can play some trick on this end. So if we want to know the maximum number of f, it also gives the large number of log f, right? Because f and log f, they follow the same trend, right? So this one equals to what? Approximate equals to and the good thing is that if you put log, all this kind of the products become sum, right? Become summation. So the then this one become n times log n minus n. Okay? Now this denominator minus sigma I ni log ni minus ni. Right? Plus ni sigma I omega I. And then look at this term. Remember? Look at this one and this one. Right? Still remember that because n equals to sigma I and I. Right? Then this term and the sum of all these terms just cancel each other. Correct? Or let me change it to more clear to make this one clearer. Right? So this term should be equal to 0, correct? This term is equal to 0. All right. Okay, so we try because by using the Sterling approximation and also by add a log on each end of on both sides of this equation, we transform this function to this function. Correct?
How the second line
Huh?
comes? The last second, how
Which
it comes?
one?
How the second line comes?
This one?
Yeah.
You just expand it.
Yeah, this.
You just put this one to here and to here. I just want to combine this term and this term to show them equal 0.
No, the second line.
Oh, this one?
Yeah.
You do the log on this end, right? You do the log on each of the term, right? Then the product becomes sum, right? Okay, so in order to find the distribution give the matrix number of microstate, we need to do the derivative of, we can do the derivative of the log f instead of f, right? They give the same result. But that's not the end of the story. Still remember, we have two restrictions. We already used one restriction, but we have another restriction. What's the other restriction? What's the two restrictions we have? I already mentioned at the beginning. Conservation of number of particles and conservation of what? Energy, right? So basically, we already used one here. So it's N is the sigma I, Ni equals to N. And we should have another one. Right? These two restrictions. We know this term equals 0, right? And for that one, we can also write it that way. We have something like this. U minus sigma I Ni equals to 0, right? So we have this one, right? Correct? So in order to bring this consideration into that equation, we need to play a mathematical trick, okay? If you feel interested, just go back home and check. I give you the keyword, you can check online why we use this way, okay? It's a little bit complicated mathematical problems, okay? So we need to introduce a kind of the factor we call is the Lagrange multiplier. Multiplier. So how it works? In order to consider the restriction, we need to bring these two considerations into this function. Okay, we already have one automatically shows up, but we do not have this one shows up. So in order to bring that one, we need to introduce we call it Lagrange multiplier. So it looks like this. Okay, it's ln f minus or plus, doesn't matter. Okay, we can call it alpha n minus sigma I, and minus beta u minus sigma I. Okay. So by introducing these two terms, we confine our maximum value of the ln f to the scope meeting these two requirements. Okay? But it doesn't change the function behavior. Remember, this term equals 0, this term also equals 0. So we just add 2 0 terms to the equation. It doesn't change too much, right? It doesn't change the value of ln f. But when you do the derivative, it changes. When you do the derivative, it changes. Because when you do the derivative, it introduces alpha and beta, right? Let's show you how it works. Okay? But why we need to introduce this term? Because we want the value we find to meet the requirement of the energy conservation and particle number conservation. Okay, and the method for us to include this consideration is by introduce the Lagrange multiplier. Okay, these two terms are called Lagrange multiplier. Okay, what's the reason for that? You can check some of the mathematics books. Okay, but anyway, so if you want to check, just remember whenever you want to bring some confinement, we need to introduce. Actually, this method always used. Have you ever been introduced this method before in other classes? If you do machine learning or AI or whatever, this one, they use this kind of expression all the time. Okay? They call them the confinement. Okay? This problem is called the confined optimization problem in the machine learning catalog. But for the thermodynamics, or physics, or mechanics, whatever, it's just called a Lagrange multiplier. Okay? The same principle. But what the principle is, check the textbook, check the mathematics books. Okay? The proof is a little bit complicated, and I don't want to spend too much time. But anyway, so then by introducing the Lagrange multiplier and by using Stirling approximation, we transform this problem into looking for the largest value, the highest value of this equation, or in other words, to find the 0 point of the first order derivative. Okay. To make the job easier, we can define a new function. We call it omega. Okay. Omega equals to ln f minus alpha and minus sigma ni minus beta u minus EI and I. Okay. Then we can do the following calculation. Okay, we spent quite a lot of time to simplify the question, to simplify the expression, and also bring the restriction, and eventually we move to this step. Okay, so what it looks like? We need to find this value. Okay, so partial Ni will equals to. Still remember the definition of the log n? Let me rewrite it here. N minus C I All right. So we'll do the derivative. The first one is just constant, disappeared. The first term disappeared, and the second term we only care about term of I, okay? Or probably let's use another label here. Probably we call it J. Okay, probably J. And then we'll consider the second term. We need to calculate the partial. I don't know. Do you know how to do the calculation of the second term? Right, the sum of all possible ni, right? But we only care about the nj times log nj term, right? So they become minus log nj and minus 1, right? Is that correct? Is that correct? And second one plus log omega j and plus alpha and plus beta. Is that right? Why I have a 1 here? Is that right? Why I have 1 extra term? Did I make some mistake here? Positive negative sign, so hold on. I think I made some mistake. Positive negative sign somewhere. Oh. Oh, I think it's right. By the way, I have the one actual minus 1. Is this correct, everybody? Do we have a negative 1 over here or not? Lord. You should use your brain, okay, not the ChatGPT. So what I'm writing here, I don't have this -1 term, but from the calculation, I think I missed something somewhere. I forgot where it is. Why I missed one term? But anyway, so we shouldn't have this term. Anyway, I will look around and check what's going on here. Okay? I will make an announcement online to see what's the mistake. But anyway, so this term should be equal to 0. All right, and then what we have is ln nj equals to ln omega j minus alpha minus beta. Okay, and from this one we will have nj equals to omega j e to the order minus alpha minus beta j. So we have the distribution give us right now we have the distribution. Okay? So if we have a total number of nj particles on energy level of Ej, then this distribution gives us the largest number of possible macrostates. Okay? Right. I will talk with the department to give us more free micro. Remember? Okay. So that means if we have a total number of particles of Nj distributed on the Ej energy level, then this kind of distribution gives us the largest number of possible macrostate. Correct? Understand what I'm saying? And this distribution, we call it the most possible or probable distribution. Okay? Okay? I mean, it's most possible or most probable distribution. Okay? Because it has the largest number of the macrostates. And this kind of specific distribution to the order of n, to the order of something, and this one we call it, and we give it the most specific name, okay? This one, this specific distribution for the IU gas, we call it the Maxwell, the Boltzmann distribution. Okay. So that means as the energy level or parking garage going up, going higher and higher, the number of particles, the number of car parking in the garage decay exponentially. Okay, decay exponentially. That's because most car probably still want to park in the first floor, and the second one a little bit less, third one even less. Okay, and it's also proportional to the how many parking spots over there. Okay, how many parking spots over there. Understand what I'm saying? That means the possibility for the particle to occupy energy level is proportional to how many open space on that specific level, as well as a distribution function to distribution function related to the energy. Okay. So we still have two questions I have not answered yet. So what is alpha? What is beta? We don't know, right? We don't know. We don't know yet. Okay. Because this is just two Lagrange multiplier we introduced during the calculation. But you can see the effect is here, okay? But how do we calculate? We have two ways to do the calculation. The first way is, since we already know the distribution, you can do something like this. Sigma I, omega I, E minus alpha minus, and E I, this one equals to total number of particles, right? And then you have sigma I, E I, omega I, E alpha minus beta E I equals to U. Okay, by solving these two equations, you can find alpha and beta. questions? No question, okay. And the other thing is, what is omega? What is omega? What is omega? Omega for ideal gas. Okay? So remember that the reason why we introduced omega is because in a tank of the ideal gas, the particles can share, particles in different places can share the same energy, right? Correct, everybody? So how many different places can share the same energy? Right? You can see that the thing is like this. We can just cut the space to small areas, right? And we define each of the small volume a parking spot. Okay, we define by the parking spot. But how small it is, we don't know, right? Because as I mentioned, no matter how small it is, we still can put as many particles on it, right? But we artificially give it a limit. We artificially give it a limit, okay? Because we want to do the calculation, right? We do not want to put 0 there, okay? We don't want to put 0 there. So in that case, we need to calculate, okay, for example, in this volume, how many different parking spots we have. Then we define that way. Omega equals to V, that's the volume of the tank, divided by H3, okay, to the order of 3. We call it 3-dimensional. Okay, H is some very tiny volume here. Okay, that very tiny volume. Okay, we cannot make it 0 because if we make it 0, then this becomes infinity, right? We don't give it the value. Okay, but any value doesn't matter. Okay, it doesn't matter what value you want. Okay? It's a random number, but cannot be 0. Okay, got my point? Then for the ideal gas, but you know that this one only depends on the volume, right? It's just like a parking garage. It's not depends on the energy. It doesn't depend on the speed of the molecule, right? For any kind of speed, they can occupy this spot, right? It only depends on the volume. Then for that one, NJ EH3. Okay. Basically, that is the degeneracy of each one. Got my point? But what is H? It's a random number, okay? Just keep in mind it's a random number. But actually, it has a specific number. Okay? It has a specific. Do you know what's the specific number of H?
Like,
A Planck constant, okay? What's the number of it?
6.6 minus 34.
6 point what?
66.
Order.
Negative 34.
Unit.
Joules per Kelvin.
What? Kelvin? I don't know. Your check. Probably not. I don't think it's right. I think the unit should be something.
The angular momentum units.
Yeah, the order of this one should be, let me see. This one should be, H should be the order of the momentum times x. So momentum is what? Momentum is the kilogram times meter divided by second and square. So this is anyway. So, but why is Planck constant? That's not a business, not our business. Okay, but just know we have a constant. Anyway, so we finished earlier today. So complicated project, so complicated calculation. That's the reason nobody have questions. Well, we have not finished the job yet, okay? So for the next time, we're going to talk about the alpha and beta. We have not finished the job. We just give the shape of the maximum Boltzmann constant. So what is alpha? Eventually, next time I'm going to show you. The alpha basically is a chemical potential, okay? And the beta equals to 1 over kT. Okay? 1 over kT. K is what? K is Boltzmann constant. T is temperature, okay? And for the next time, we will eventually get the expression of the entropy, okay? Entropy equals to K times ln the omega. Okay? Omega is the punctual adjustment. So that's the number of the microstates corresponding to a distribution. So this is the job we're going to do next time.
We're mixing the water in two tanks. Why do we use? Would the volume also stay constant?
Yeah, that's the reason for the water. The constant volume and constant pressure, heat capacity roughly the same. For liquid.
Oh.
But for gas is different. For liquid, it's probably roughly the same.
So
that's the reason.
is it okay to just say C or just say C?
We don't. And in the future, I mean, when we go to the metal or like alloy or whatever, we even not distinguish the two types of free energies. One is the heat free energy, the other is the Helmholtz or Helmholtz free energy. The difference for the ideal gas, they're very different, but for the solid, it's roughly the same.
And could you remind me again why they're both T1 plus T2 over 2? I know that I asked you, but I forgot about it again.
When they reach the thermal equilibrium, they exchange, for example, T1 and T2. They need to change the heat, right? And then the final temperature, T1 minus the final temperature should equals to times the capacitance should be equal to delta Q, right?
Yeah.
And for that one, the T final minus T2 times Cp also need to delta Q. This one release energy, this one absorb energy, right? The heat. Just
Delta Q must be the same.
yeah, this will be the same. Right?
So
I did not say delta the same. I'm saying the final temperature, right? The final temperature should be the same.
So it's like this tank gives delta Q to this tank.
Yeah.
Instead of this tank loses delta Q and that tank gains delta Q when mixed.
The same, yeah. I mean, this loose is gain, so that's the same thing. It doesn't matter.
So there's only one delta Q.
Yeah.
Instead of like I cool this down
Oh,
the large tank.
when you
with
want,
delta
yeah,
Q and
when you
other
calculate,
delta Q.
when you calculate the entropy change, yes, you need to separate them. For the entropy calculate, to calculate the change of the entropy. But when you calculate the final temperature, this is the actual physical process. You need to just the delta Q is there, right?
So like, can I, if you make this one like TF, and this one is also TF, and then you mix them together, and this loses delta Q1, and that gains like delta Q2. Like if I were to think like this way, then how do you show that those two delta Qs are the same?
These two delta Q are not the same. So the, yeah, they're the same, they're still the same. Yes, they're still the same. That is still the same, no problem.
Is it just this divided by 2?
Yeah. Yeah, that's still the same. But remember, we'll calculate the entropy change. It's something like this, right?
Yeah.
Although this term is the same, but this term not the same. Because temperature different,
Yeah.
right? So that's the reason the entropy change. Yeah, I mean, the same thing. I mean, if you exchange the energy with the larger time, the delta is still the same.
Mhm.
Yeah.
Thank you.
Why do we have one? I need to recheck it.
Oh, I'm just asking if I go to my lab, so like more campus, may I take classes from online sometimes?
Yeah, you can.
So how to join the class?
There's no way to join online, but whenever we finish the class, the video of the class or footage of the class will automatically upload to the it's called web course at UCF. You just go to the it's called My UCF account,
Okay.
and then on that account you will find web course at a link at UCF on the left side of the screen. Click that one,
Okay.
and then in that one you can find another link called the Panapto or something. Napto or something, I forgot the name, but it's really weird name. It's called Panapto or Panap, I don't know, potato, whatever.
Okay.
Panapto, Panapto video, you can find all the footage of.
Okay. And I have one question regarding the exam. Is this open book exam?
It's open.
So the hard copy of that book maybe we don't have. If we turn off our Wi-Fi, can we use a laptop soft copy of that book?
I have no control on it. You take home exam.
It's home exam?
Yeah.
Oh, okay. Thank you. It's sometimes difficult, but actually I'm enjoying your class.
Yeah.
Thank you.
Why I have one actual stuff or what's wrong with the calculation?
Bye, Prof.
Oh, I see.